Today we'll consider question 5 out of chapter 1.2, which reads as follows. Show that in an abelian group, the mapping A to AN for a positive integer n is a group homomorphism. Find an example of a non-abelian group for which this mapping is not a group homomorphism. Take a couple seconds to try this out for yourself, then we'll look at some hints, then we'll move on with the proof. Alrighty then, for some hints, we'll start with the second hint first, which is a little easier, which is just, let's consider an example of a non-abelian group, which from a previous problem was claimed to us to be S3, or the rotations of a equilateral triangle. This is an example here, and then another hint is that we want to prove this is true for a positive integer n, where the choice of n is arbitrary. So since it needs to be arbitrary n, we somehow need to prove that it's true for all n, such that our choice doesn't matter. So with those hints, and perhaps a final hint being that since you're trying to prove it for all n, or we're using positive integers n, we should be considering doing induction somewhere. Since if we're proving for all integers, then we're probably going to need to induct. All right, give it another shot, and then we'll go on to the proof. All right, let's go on with the proof. So I think it'll be easier to just show the non-example first, where we let phi, being our mapping of interest, sends a to a cubed. And on this, we're going to show, we'll recall that a mapping is a group homomorphism if phi of AB is equal to phi of A times phi of B. And so for our example, let's consider phi of RR, where R is used using the notation on the right. Well, we consider this first as the product phi of RR, which will be of the form phi of R2, since R times R is R2, as you see in this table here. Alternatively, we can check the product phi of R times phi of R. Well, phi of R is going to be phi of R cubed. That's going to be R times R is R squared, and then R times R squared. R times R squared is just the identity E. So this is going to equal E times E, which is equal to E. Meanwhile, phi of R squared, R2, which is R times R, is going to equal, is going to be R2 cubed. So that's going to be R2 times R2, and then times R2 once more. So R2 times R2, if we check our table, is FR. But FR times R2 is FR2. FR2, another transformation that is not the identity. So we see that phi of RR is not equal to phi of R times phi of R, and therefore this mapping is not a group homomorphism. So let's go back and prove it for abelian groups. For abelian groups, there are two ways to do it. You can first choose an n and then try to prove it that way, but let's do and then you'll have to do your proof by induction later. For now, let's just do it in an easier way, and let's assume, first let's prove the base case, namely that phi 1 of AB is equal to phi of A times phi of B, where phi 1 is the mapping which sends an element A to A to the first, or namely to itself. Well, phi 1 of AB is just AB, and that is clearly equal to A times B. So we have our base case done for our induction. Next, let's assume that phi n is a group homomorphism in the sense that it respects products, such that this equation would be true. We'll now show that this implies that phi n plus 1 also respects it. And let's set phi n plus 1, we're just going to denote that as phi n tilde, where phi n tilde has the property where phi n tilde of some number x is equal to x times phi n of x. And this is clearly well defined. So with that, we're going to see that we're not going to prove that phi n being respecting multiplication implies that phi n plus 1 respects multiplication. So let's consider phi n plus 1 of AB less than or equal phi n tilde of AB, which is just going to be AB times phi n of AB. Phi n of AB, we assumed respected multiplication. So this is equal to AB times phi n of A times phi n of B. And now we apply the abelian property of the group 1s to swap B and phi n of B, since phi n of B is a element of the group, since groups are closed under their operation. So we're simply going to swap those. We're going to get A times phi n of A times B times phi n of B. And we'll note that these are just our definition of phi n tildes, or we'll say this is phi n plus 1 of A times phi n plus 1 of B. And we've shown that phi n plus 1 of AB is equal to phi n plus 1 of A times phi n plus 1 of B. So we see that this is true for all n. So this mapping is indeed a group homomorphism. With that induction complete, we're done with our proof, and with our example, we're done with the question. So thank you for watching.